그러면 여기 하고. Okay. We continue for section 9.3, alternating series and absolute convergence. Okay. So, in the earlier section, we haven't considered the series which has the sign changes, which we often meet in the real life. This type of series is called the alternating series, if sign changes alternatively, one at a time. Okay, in this case, we use this alternating series test. So, suppose we have an alternating series like this, then this is convergent if it satisfies these two conditions. First, the sequence should be decreasing. Without this sign, the B and BI terms should be decreasing. Next, the nth term should converge to 0. If those two conditions satisfies, then we can always conclude that the given alternating series is a convergent series. Okay. Okay. As Mr. Kim mentioned, that these two conditions should satisfy together. And this proof shows why those two conditions both of the conditions are needed. In this proof, we consider the S of 2n and S of 2n plus 2 to find the general term S of 2n, which can be written in this way. S of 2n plus 1 can be written as S of 2n plus b 2n plus 1. Here, the limit of S 2n plus 1 can be written as this one and that one. In this case, from the given condition, we know this limit of b of 2n plus 1 goes to 0 by the second condition. So we have this. So we will see these two should be same. What that means? What that means is the partial sum of even and odd orders tends to the same limit s. That means the series convergent. You understand? Okay, so the partial sum of odd and partial sum of even numbers converge to the same limit, so the series is convergent. So that's very useful test to check the convergence or divergence. Okay, so first example for this section is finding to test the convergence of the alternating harmonic series like this. 1 minus 1 over 2 plus 1 over 3 minus 1 over 4 like this. We can easily check. These Bn terms are decreasing. Okay, because 1 over n plus 1 is less than 1 over n. And this Bn converges to 0. So since these two conditions satisfies, this harmonic alternating series converges. But for the second example here, from here, this Bn term does converge to what? 3 over 5. So it violates the second condition of the alternating series test. So it does not. So it does not converge. So it's divergent. It diverges. And next thing is the next definition is absolutely convergent. A series is called absolutely convergent if summation of absolute of an is convergent. Okay. And the series summation of an is conditionally convergent if summation of an converges but summation of absolute of an diverges. Okay. So if a series summation of an is absolutely convergent, then the given series is convergent. We can easily draw the theorem 3. Here is the example. Is the series summation of sine n over n cube is absolutely convergent? Let's check it. Take the absolute value of these Bn terms. Okay. And then this the general term. Then sine of n is always less than or equal to 1. So we can easily find this inequality for all n greater than or equal to 1. Okay, but the summation of this one converts by the P series test, so we can say the summation of this one also converts. So the absolute value of the AN's terms and summation of those converge, so it is the original series is absolutely convergent. Next test is the ratio test, theorem 4, ratio test. The ratio of the limit of the absolute value of ratio is equal to 1, is converged to L, which is less than 1, then the AN plus 1 over AN of limit converges to L, which is less than 1, then summation of AN is absolutely convergent. So it is convergent. The limit of this is equal to n, is L is greater than or equal to 1 or infinity, then the series diverges. If the limit of absolute value of AN plus 1 over AN is equal to 1, then we cannot say anything yet unless we use other method to check the convergence or divergence. So this ratio test gives us a pretty clear criteria, the first step to check the convergence or divergence of the given series. So this ratio test is one of the easiest methods to check the convergence or divergence. But we often meet the third case. So when we meet the third case, whose limit is equal to 1, then we have to use all the methods that we have learned so far. Okay. So investigate the convergence of the series of this one. So compare these two terms, and then we see it goes to 1 over 5. So in this case, it's less than 1, so it converges. It's decreasing rapidly, but that's what that means. For this term, AN is like that, so the absolute value of AN plus 1 over AN goes to 2 when n goes to infinity. So it's bigger than 1, so we can easily say this series diverges. Okay. Investigate the convergence of series of this n square of 1, like this. Then we can, now as I mentioned before, the limit is going to 1. So with this ratio test, we cannot conclude anything on that, even though we already know the summation of n over n square, 1 over n square converges. But with this ratio test, we cannot say anything. Also, for the summation of 1 over n, same thing. The limit is equal to 1. So even though we know the summation of 1 over n diverges, with the ratio test we cannot say anything. So in this case we use a p test to say this divergent. Also we say for this example we use the p test to say this convergent. And root test next. Root test. This is also one easy way to test it. This test is useful, very useful when we have a function which has nth power. Nth power. If a nth term has the power of n, then it is convenient to apply. In that case, we take a nth root of the absolute value of an term. Then find the limit of it. If the limit is less than 1, we say the series converges. Absolute converges. Okay? And if the limit is bigger than 1 or infinity, then we can say it is a divergent series. But if it is equal to if limit is 1, then this root test is also inconclusive. So we have to use other the test to check for this case. Okay. So 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 in case that you have the third case, then we can use other method to check it. So first example 8 show about this one. If you take a nth root, because it's the nth power, so if you take a nth root, then you can easily find the limit of this function, this term, and which is less than 1. So we say the series converges by the root test. But for the second example, which is summation of -1 n to the n plus 1 times 1 over ln of n. In this case, we can show, this case we have a, okay. Now this example 9 is a very typical example for to check the alternating series test. So this given function which has alternating term, so we define a series first and then check for the assume for any the fixed positive number, capital large N, and check the given series, the Bn's term of the given series, alternating series is decreasing. So we check whether it is increasing or decreasing. Then we can check, we can easily see it is true. And then next, find the limit of the nth term, Bn's, limit of Bn. It gives us the 0 as the limit of the Bn term. So it satisfies two conditions of alternating series test. So we can conclude the given alternating series converges. Okay. So this is a very typical code for checking the alternating series test for any problem. If you change the function here, for general, any of the earlier examples, if you change this function with the function, the series and the Bn terms of the early alternating series from the examples, then you will see easily the same conclusion that you had. Okay, and most of the examples and solutions from the exercise problems can be found in this web site, and with the solutions and the code, so you may check it and you can get prepared for the presentation of your problems. I think that's it for the section 9.3. So before we start section 9.4, do you have any questions?